Section 24, Cosmological History of Our Universe. This section was updated March of 2025. History of our universe in 15 seconds. First there was nothing, then there was something, then there was hydrogen, then there was dirty hydrogen. First the dirty hydrogen was ionized, then it was neutral, then it was ionized again. Here is a beautiful and useful visualization of the cosmological history of the universe. Time increases left to right. At specific times, a circular hoop is drawn, and we see the general state of the universe at that time. The radius of the hoop is a very loose representation of the scale factor at the time, so of the expansion of the universe. This helps us to see different epochs and how the distance between distant galaxies has increased over time, but it is not a timeline of individual galaxies. Now, let's learn the detailed history of our universe from beginning to present to future. This graph shows the scale factor, the green curve, versus time for the entire history of our universe plus 120 billion years into our probable Big Chill future. The horizontal scale is the logarithm of time in seconds since the Big Bang, from minus 50 on the left to plus 20 on the right. Here is 1 second, and here is now. The vertical scale is the logarithm of the scale factor, from minus 60 at the bottom to plus 10 at the top. The scale factor now is 1, so 0 on this scale, log scale. We can also read the average photon energy in electron volts on the orange scale on the right side. For the middle portion of the green curve, expansion is dominated by radiation, and the scale factor is proportional to the square root of time. So, on this log scale, moving 20 units to the right increases the log of the scale factor by 10 units. So, 20 units, 10 units. Let's recap some of our universe's past. There will be new information about particles and forces for the first millisecond. For times after 1 millisecond, this will be a limited repetition of material we have already covered in the course. So for more information, go to the other sections of the course. In this section, I will say the universe as much as our universe. I always mean our universe. I am not talking about different possible universes in this section. We will use Big Bang for the start of our universe before the Planck time, not the end of cosmic inflation and not CMB last scattering. We will start with the Big Bang and move forward in time. So, lower left to upper right. All times will be time since the Big Bang. At the Planck time, here, 5.4 by 10 to the minus 44 seconds after the Big Bang, at the lower left of the green curve. The universe was extremely hot and dense. Temperature was 10 to the 32 Kelvin. Radiation average particle energy was 10 to the 16 tera-electron volts. Though whatever particles existed then were not photons. Before and at the Planck time, quantum mechanical effects and quantum field theories should have been as important as gravity. Space-time then may have fluctuated wildly, perhaps like a foam, not like our orderly spatial coordinates. The gravitational force between elementary particles would have been as strong as the strong nuclear force, not weak as it will shortly be. General relativity must be replaced with a verified theory of quantum gravity, but we don't have a verified theory, so physicists do not know what happened in that regime. The time before the Planck time is called the Planck epoch or Planck era, and there are no testable theories for this regime. You can read more about the theory of everything, TOE. This is shown below the green curve as the red time period, TOE, before the Planck time. You may see articles suggesting that our Big Bang may have begun as a seed in an older, larger universe. It seems unlikely that there ever could be evidence for anything before the Planck time. You may also see multiverse articles suggesting that our Big Bang is the result of our brain crashing through another brain. I don't believe there is any evidence for this. Temperatures in the early universe were far higher than in our particle accelerator collisions. Temperatures will remain higher than particle accelerator collisions until about a trillionth of a second after the Big Bang, around here. The theoretical physicists have theories for particles and forces after the Planck time, but conditions at these early times cannot be verified by physics experiments on Earth. This is part of the reason why we do not have a verified theory of quantum gravity. The only place in the universe with conditions perhaps comparable to the Planck time is the presumed singularity inside a black hole's event horizon, but we cannot see those. Our observable universe is a small or perhaps infinitesimal part of our universe that began with our Big Bang. Though the radiation particle energy density and average energy would have been immense at the Planck time, it can be calculated there would have been only one single radiation particle within the cosmic particle horizon volume at the Planck time. I don't mean one type of particle, I mean one single particle. But that would mean that our universe cannot be considered smooth at that Planck time, and therefore general relativity, which assumes smoothness, is not valid at that time. We need quantum gravity. Since general relativity would not have been valid under those conditions, this calculation is also not valid at the Planck time. So our models are not valid at or before the Planck time. Supplemental video number 7 discusses Planck units. At the Planck time, there was a symmetry breaking such that general relativity became separate from quantum mechanics and quantum field theories, and gravity became much weaker than the other fundamental forces. But the other forces remained grand unified, shown as the gold time period here after the Planck time. So gravity had separated. At some time, general relativity becomes fully valid. Then we can use the Friedmann equations, assuming its assumptions of homogeneity and isotropy were valid. At that time, all particles were massless and traveled at the speed of light, though there were no photons, no light yet. Any particles then were relativistic and expansion was dominated by radiation. The scale factor was proportional to the square root of time, increasing but decelerating. the cosmic particle horizon distance at those times was twice the speed of light times the time since the Big Bang or Planck time. It is assumed that there were quantum mechanical energy density and temperature variations throughout the universe that began with the Big Bang or the Planck time. And perhaps the universe, our universe, had non-zero curvature, positive or negative curvature, at that time, though it is close to zero, flat, today. In section 23, we discuss this flatness problem. Prior to 10 to the minus 36 seconds, the electroweak forces and the strong nuclear force are believed to have been unified, grand unified, and elementary particles were different in that grand unified epoch than later or today. You can read more about the grand unified theory. At 10 to the minus 36 seconds, here, the temperature had fallen to 10 to the 28th Kelvin. Radiation average particle energy was 10 to the 12th tera-electron volts. At 10 to the minus 36 seconds, there was another symmetry breaking such that the strength of the electroweak forces fell below the strength of the strong nuclear force. They were no longer grand unified. So here's the strong force, and here's the electroweak force. They have separated. Perhaps there were quarks, gluons, and color charge after this time, but those particles were massless for the time being, traveling at the speed of light, relativistic. Perhaps there were Higgs bosons then as well. If so, I don't know if they had mass at that time. The electromagnetic force and weak interaction were much different in the very early universe, before 1/1,000,000th of a second, than afterward. They were combined into the electroweak, hypercharge, and isospin forces. Elementary particles then were massless and traveled at the speed of light, but they had different characteristics than 1/1,000,000th of a second later or now. Physicists do not know for certain because this energy regime at 10 to the minus 36 seconds is 1,000,000,000 times higher than for the Large Hadron Collider. Expansion is presumed dominated by radiation, but the particles were different than photons at this early time. Physicists believe that the symmetry breaking at 10 to the minus 36 seconds that split the strong nuclear force and the electroweak interaction may have created topological defects, which could not be created thereafter at lower temperatures. One possibility for the topological defects is magnetic monopoles, an isolated magnetic north or south pole. The point-like topological defects are predicted to have had rest mass energy around 10 to the 12th tera-electron volts, a particle mass then comparable to a bacterium now. If topological defects had been created, expansion of the universe would have become dominated by the matter energy density of the topological defects, beginning around 10 to the minus 16 seconds if radiation dominated expansion up to that time. No magnetic monopoles have been detected by physicists, and cosmologists are virtually certain that expansion was never dominated by the matter energy density of topological defects. In section 23, we discussed this magnetic monopole problem, whose solution comes next. Sometime before 10 to the minus 32 seconds, cosmologists propose that there was an accelerating exponential expansion, shown here, called cosmic inflation. The universe is thought to have expanded by at least 26 orders of magnitude in 10 to the minus 34 to 10 to the minus 32 seconds, much faster than the speed of light. Once cosmic inflation ended, expansion was dominated by radiation again. Any initial curvature of the universe became greatly reduced by cosmic inflation to nearly zero, and then increased again slowly with expansion of the universe, dominated by radiation and then matter. This cosmic inflation is cosmologists' solution for the flatness problem. Why we see zero or nearly zero curvature today when it need not have been zero after the Planck time. Cosmic inflation reduced the number density of pre-existing topological defects to such a low value that the present number density would be less than 1 in our visible universe. The cosmic inflation is cosmologists' solution for the magnetic monopole problem. Why physicists don't find any magnetic monopoles and why they never dominated expansion. In section 19, we saw that the cosmic microwave background has uniform temperature in all directions to within 30 parts per million. In section 23, we saw that this uniformity of temperature presents a problem, the horizon problem. How could different regions have been in causal contact and thermal equilibrium from early times? This cosmic inflation is cosmologists' solution for the horizon problem. Cosmic inflation increased the cosmic particle horizon distance at the time of CMB last scattering by at least a factor of 164, such that the regions within our visible universe had been in causal contact at early times. This also increased our present particle horizon and radius of our observable universe from 14,200 megaparsecs had there been no cosmic inflation to at least perhaps 109,000 megaparsecs if there had been cosmic inflation of 26 orders of magnitude. During exponential cosmic inflation, energy density fluctuations from the Planck time kept a constant fractional amplitude. Cosmologists propose that the inflaton field that caused cosmic inflation would have had quantum fluctuations of the right magnitude to leave fluctuations in radiation energy density after inflation here that would later produce the initial fluctuations in dark matter density about here that would later produce the 30 part per million fluctuations of the cosmic microwave background temperatures here that we see now here. As far as I know, there is no direct evidence for or against cosmic inflation, but there is good indirect evidence from Planck satellite data, as well as it solving those three problems. Cosmologists are seeking stronger confirmation in cosmic microwave background polarization measurements, B modes. During cosmic inflation, radiation temperature fell either drastically or significantly, but was then reheated at the end of cosmic inflation to its temperature prior to inflation. I have not read anything about particle physics during the inflation period. Once reheating completes, so by 10 to the minus 32 seconds, the radiation temperature is once again inversely proportional to the scale factor for the remainder of the history of the universe. Particle densities plummeted to near zero during cosmic inflation, which is how the magnetic monopole problem got solved. When inflation completed, reheating caused particle pairs to be created to repopulate the universe to the pre-inflationary densities and temperature, except that magnetic monopoles and other topological defects could not be created after cosmic inflation, and their density had diluted to near zero. Some authors use the end of reheating after cosmic inflation as their Big Bang time, rather than the time before cosmic inflation or before the Planck time. And some other authors use the CMB photon decoupling and last scattering as their Big Bang time. At the end of cosmic inflation, the strength of the electroweak forces was 1/100th of the strength of the strong nuclear force. All elementary particles, including quarks, had zero rest mass at this time. But quarks and gluons did have color charge, so perhaps quarks had some effective mass due to their clouds of gluons. I don't know. After cosmic inflation and for the next 50,000 years, the expansion of the universe was dominated by radiation, elementary particles moving through the universe at or near the speed of light. Radiation energy density was proportional to 1 over the 4th power of the scale factor. The scale factor was increasing proportional to the square root of time, increasing but decelerating. Radiation energy density was decreasing proportional to 1 over the square of time. If magnetic monopoles or other topological defects were created when the strong nuclear force separated from the electroweak interaction at 10 to the minus 36 seconds, and there had been no cosmic inflation, then expansion of the universe would have been dominated by the matter density of the topological defects from 10 to the minus 16 seconds onward. This did not happen for our universe, attributed to cosmic inflation, though perhaps they had never been created. So expansion continued to be dominated by radiation. With cosmic inflation completed, I am switching to a log-log graph of radiation temperature, the green curve, in Kelvin versus time in seconds after the Big Bang. The horizontal scale is the logarithm of time in seconds since the Big Bang, from minus 30 on the left to plus 20 on the right. Here is 1 second, and here is now. The vertical scale is the logarithm of the radiation temperature in Kelvin, from minus 5 at the bottom to plus 25 at the top. We can also read the average photon energy in electron volts on the orange scale on the right side. The radiation temperature was decreasing, proportional to 1 over the square root of time, while radiation dominates expansion. So moving 10 units to the right reduces temperature by 5 units. Here's 10 units, 5, 10, 5, 10, 5, 10, 5. After cosmic inflation, Radiation temperature falls as the universe expands, as does the energy density and pressure of radiation and, later, matter. At 10 to the minus 12 seconds, here, a trillionth of a second after the Big Bang, the electroweak scale, the temperature and radiation particle energy fell to about 10 to the 16 Kelvin and 3 tera-electron volts. This is within the energy range of the Large Hadron Collider, so particle physics is pretty well understood and verified as of that time. The radiation particle energy is falling below the mass of the Higgs boson. The Higgs field turns on, breaks electroweak symmetry, and gives most elementary particles, including quarks, their mass and their electrical charge. It may be that neutrinos did not get their mass from the Higgs field, but that won't concern us. The color charge of quarks and gluons probably existed before this time. The prior electroweak hypercharge and isospin forces became replaced with our present electromagnetic force and weak interaction. Now there were photons. The weak interaction became much weaker than the electromagnetic force and extremely short-ranged versus the infinite range of electromagnetism and photons. After that time, ordinary matter elementary particles and forces had the same properties and values as they do today, though nothing is yet known about dark matter particles. Now there were photons, neutrinos, electrons, and quarks as we know them today, and antiparticles, but not yet protons and neutrons, which are composite, not elementary. At 10 to the minus 11 seconds, all the standard elementary particles and their antiparticles were continuously created in pairs as the average photon energy was higher than the particle rest masses. For the next 100 microseconds, everything that occurs is in the realm of elementary particle physics. If this is new and strange to you, don't worry about the details, though I will try to present the timeline accurately as I understand it. After 10 seconds, the particle physics will be finished. At 10 to the minus 11 seconds, all standard elementary particles were relativistic. The numbers of each particle and antiparticle were comparable to the number of photons. On this diagram, the vertical axis is particle rest mass. Temperature and average photon energy are falling rapidly. As the first microsecond progresses, the highest mass elementary particles and antiparticles no longer get created and they annihilate. The top quark, the Z boson, W boson, bottom quark, and tau disappear. At 1 microsecond, there were not yet protons and neutrons. There was a hot, dense, liquid-like quark-gluon plasma whose density everywhere in the universe was higher than a proton's density today, much denser than a nucleus or a neutron star. Physicists have produced and studied quark-gluon plasmas at the Large Hadron Collider at CERN, shown in this green bubble, and the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Lab, shown in this blue bubble. There were also electrons and positrons, muons and anti-muons, neutrinos and antineutrinos, all in numbers comparable to the number of photons. At 1 microsecond after the Big Bang, so about here, the temperature and average photon energy fell to about 10 to the 13 Kelvin and 3 giga-electron volts. If dark matter consists of elementary particles, and if they were created by neutrinos or via the weak interaction, this probably occurred in the first microsecond, but physicists presently have no information. By 10 to the minus 4 seconds, charm and strange quark-antiquark pairs stopped being produced and annihilated. About 10 to the minus 4 seconds, 100 microseconds, the temperature and average photon energy fell to 1.3 by 10 to the 12th Kelvin and 300 million electron volts. Energy density fell by a factor of 10,000 since 1 microsecond. The high temperature, high density liquid-like quark-gluon plasma throughout the universe became less dense than a proton's internal energy density. The quarks and gluons underwent a phase change from quark-gluon plasma to now a plasma of individual hadron particles. 3 quark baryon particles and antiparticles, such as protons and antiprotons, neutrons and antineutrons, and 2 quark mesons, such as pions, not shown here. This phase change is a kind of freeze-out, though very hot. The temperature was now low enough that proton-antiproton pairs, neutron-antineutron pairs, and pion-antipion pairs annihilate and are not recreated. Quarks and antiquarks are believed to have been continuously created in pairs, equal numbers, since the early universe and since cosmic reheating, continuously annihilating in pairs and being recreated in pairs. At 1 microsecond after the Big Bang, their number and energies would have been comparable to the number and energies of photons. When temperature falls low enough in the first millisecond, the simple case would be that all the quarks and antiquarks would annihilate in pairs, equal numbers, leaving 0 quarks, antiquarks, protons, neutrons in the universe for the remaining lifetime of the universe. No hydrogen, no stars, no Earth. However, somehow, shortly there would be a small residue of protons and neutrons and no more antiprotons and antineutrons. Somehow, 1 out of a billion antiprotons did not annihilate with a proton, but perhaps decayed to a lepton, an electron or muon. This violated conservation of baryon number, but kept the universe electrically charged neutral. This left some protons to survive with an equal number of electrons. This process is called baryogenesis. Physicists know the 3 conditions required to cause this, some of which have been observed in particle collider experiments, but they do not know the specific mechanism and process at work in the first millisecond of the universe. From 10 to the minus 4 seconds to 1 second or 10 seconds is sometimes called the lepton era or lepton epoch, as the dominant ordinary matter particles were relativistic muons, electrons, and neutrinos and their antiparticles after most quarks and baryons annihilated and were no longer produced. Before 1 millisecond, muon-antimuon pairs ceased to be produced and annihilated. Around 1 second, neutrino-antineutrino pairs cease to be produced. Neutrinos do not interact with photons and are not created by photons. Neutrinos and antineutrinos interact with electrons, positrons, protons, etc. via the weak interaction, which, no surprise, is weak. Around 1 second, with densities falling, the interaction rate fell below the Hubble parameter rate of expansion of the universe. Neutrinos had decoupled, freeze out, from other ordinary matter particles, electrons and positrons. It is not that average photon energy fell below the rest mass of the neutrinos. It did not. But neutrino-antineutrino pairs could no longer annihilate because their relativistic energy soon fell below the electron rest mass. These primordial cosmic relic neutrinos and antineutrinos have been traveling the expanding universe since the first second, losing energy due to cosmological redshift, and have played no further role for most of the life of the universe. Neutrino rest mass energy is much smaller than an electron, so neutrinos were relativistic and count as radiation for most of the age of the universe, but count as ordinary matter today. Cosmologists would like to detect these relic cosmic neutrinos to shore up the model for the first second after the Big Bang. For example, is the present cosmic neutrino temperature identical in all directions? These cosmic neutrinos are passing through your body every second of your life. If dark matter consists of elementary particles that are weakly interacting massive particles, WIMPs, not axions, they probably decoupled from neutrinos and ordinary matter around 1 second. Two seconds after the Big Bang, here, the energy density of radiation, photons and neutrinos, was 1,000,000 times the energy density of matter, and 82,000 times at 5 minutes, which is here. So radiation still dominated expansion of the universe. There were protons and neutrons, but all antiprotons and antineutrons were gone by then. At 2 seconds, the temperature was 600 times hotter than the core of the Sun today, but the density of protons and neutrons was 2% of the density of water today. From 2 seconds to 5 minutes, all neutrons became bound with protons, first as deuterium nuclei, and then as helium-4 nuclei, with only a small amount of deuterium, helium-3, and lithium. This is called Big Bang Nucleosynthesis. No carbon, oxygen, or nuclei heavier than beryllium were produced. We covered this in more detail in the main course. At the end of Big Bang nucleosynthesis, the ordinary matter mass fraction of hydrogen-1 single protons is 76% and helium-4 is 24%. The ratio of deuterium to hydrogen-1 is around 25 parts per million. Helium-3, lithium-7, and lithium-6 are also present in smaller amounts, but no carbon or oxygen. This will be the starting composition of the first stars when they form later. The mass fractions are an important source of information for confirming the hot Big Bang and understanding the parameters of our universe. In the first 5 minutes of the universe, there was neither sufficient time nor matter density to produce carbon. 2 seconds after the Big Bang, the average photon energy was 2.2 million electron volts, gamma rays, which could still create electron-positron pairs. For every proton or neutron, there were about 1 billion electrons and antimatter positrons. They were relativistic and counted as radiation, not matter, for driving expansion. By 10 seconds, the temperature had fallen to the point where electron-positron pairs ceased to be produced and they annihilated, producing gamma rays. Though electrons and positrons were believed to have been created initially in equal numbers and should have annihilated in equal numbers, leaving 0 electrons in the universe, somehow there was a small residue of negatively charged electrons, exactly balancing the positive charge of the residue of protons, so the universe as a whole was electrically neutral. This is called leptogenesis. I think of this as a consequence of baryogenesis, with some antiprotons decaying to electrons, but I am not a physicist. Soon thereafter, the electrons were non-relativistic and counted as matter, not radiation. The temperature is still hot, so the nuclei and electrons are in an ionized plasma state, not neutral atoms. Cold dark matter was 84% of total matter, as it is today. The cosmological properties of dark matter are inferred. It has not yet been detected directly. The adjective cold means non-relativistic when the universe was tens of years old, such that it did not count as radiation from that time forward. Dark means rarely, if ever, interacting with light or with ordinary matter. Scientists do not know what dark matter consists of, when it was created, or if it has ever interacted with light, ordinary matter, or itself, other than through gravity. Radiation energy density was proportional to 1 over the 4th power of the scale factor, and non-relativistic matter energy density was proportional to 1 over the 3rd power of the scale factor, a faster decline for radiation than for matter. At 50,000 years, here, temperature 9400 Kelvin, the energy density of radiation falls below the energy density of matter, and expansion of the universe is then dominated by non-relativistic matter. The scale factor was now increasing roughly proportional to the 2/3 power of time, increasing but decelerating. Matter energy density was decreasing, proportional to 1 over the square of time. The radiation temperature was decreasing, proportional to 1 over the 2/3 power of time. From 220,000 years to 370,000 years, here, the radiation temperature cooled from 4,000 Kelvin to 3,000 Kelvin. Over this period, protons and electrons combined to form neutral hydrogen atoms. This is called recombination, even though they had never previously been combined. Neutral helium atoms had already formed. The universe was no longer a plasma scattering the photons, and so then photons could stream freely through the electrically neutral expanding universe. We see these final last scattering photons today as the cosmic microwave background, having been redshifted by a factor of 1090 since they were emitted at that time. Our current visible universe was about 25 megaparsecs in diameter when this light was emitted at CMB last scattering. In section 19, we discussed CMB fluctuations, dark matter overdensities, and baryon acoustic oscillations, BAO, and how CMB and BAO measurements are an important source of information for understanding the parameters of our universe. That last scattering light soon redshifted from visible to infrared, and there were no stars yet, so this is called the dark ages. While ordinary matter was still an ionized plasma, slight overdensities of dark matter began to contract relative to the expansion of the universe and pulled ordinary matter along to contract. Spatially small overdensities would later form galaxies with stars. The first stars were massive, fused hydrogen rapidly, and began to shine sometime around 50 to 100 million years after the Big Bang, around here. The star's ultraviolet light reionized the hydrogen atoms to protons and electrons, first near the stars, then in the galaxy, then near the galaxy, and ultimately the entire universe, including the cosmic voids. This is the epoch of reionization, which completed by 1.2 billion years. The plasma density was now low, so mostly transparent to cosmic microwave background photons, optically thin. The scattering rate of photons off electrons was lower than the Hubble parameter expansion rate of the universe. The mean free path was larger than the Hubble distance. About 1 out of 16 CMB photons have scattered off the reionized hydrogen, so there is some irreducible fuzziness to the CMB imaging. Nearly every non-dwarf galaxy is believed to have at its core a rotating supermassive black hole of mass several 100,000 to billions of solar masses. Cosmologists do not know when those black holes initially formed. Were there intermediate mass black holes somehow before the first stars formed? Gas and shredded stars spiraling toward the black hole event horizons, an accretion disk, heats up and high-energy particles escape in two jets in opposite directions. Early in the life of a galaxy, the jets can be brighter than the stellar core of the galaxy. These cases are called quasars, or active galactic nuclei, AGNs. Over time, the immediate area of the black hole gets cleared out. More information is available in the course on gravitation and black holes. Dark energy presently appears to be a small, constant, or nearly constant energy density of space in the universe. Not a constant amount of energy in the expanding universe, but a constant energy density. Perhaps it is a built-in property of our universe. Perhaps it is the energy density of the vacuum of space. Perhaps present cosmological assumptions and theories are wrong. If dark energy density has been constant over time, then at 7.6 billion years, 6 billion years ago, somewhere in here, the energy density of matter fell to twice the dark energy density. Prior to this time, the scale factor was increasing but decelerating. After this time, the scale factor is increasing and accelerating. This is the accelerating expansion of the universe due to dark energy. At that time, the scale factor was 0.61, redshift Z was 0.64, and the radiation temperature was 4.5 Kelvin. At 10.2 billion years, 3.6 billion years ago, where this red line is pointing, the energy density of matter fell below the constant energy density of dark energy. At that time, the scale factor was 0.77, redshift Z was 0.3, and radiation temperature was 3.6 Kelvin. Dark energy has dominated the accelerated expansion of the universe since that time. Expansion has accelerated and is expected to become exponential in the future, increasing by a factor of 10 every 40 billion years if dark energy density is constant, independent of time and scale factor. Cosmologists refer to this case as W equal -1. Presently, it looks like our universe will continue to expand forever. The distance between distant galaxies will continue to increase, but the galaxies themselves will remain intact galaxies, and galaxy clusters will remain galaxy clusters. The distance between galaxy clusters will continue to increase. This future is called the Big Chill. Stars in our galaxy will continue to age. The Andromeda Galaxy will merge with the Milky Way. But galaxies beyond our local group will appear dimmer and redshift into the infrared in future. There will be no end to time, but the cosmic microwave background temperature will get colder and colder over time. Galaxy superclusters are not gravitationally bound and will separate with time. The green curve is for the case of constant dark energy density. If dark energy density decreases with scale factor, but W is more negative than -3 and less negative than -1, our universe will still end with a big chill, but the time evolution will be slower. If dark energy density increases with scale factor, W more negative than -1, the increasing energy density of dark energy will eventually rip galaxies apart, then rip stars apart, then rip all matter apart. This possibility is called the Big Rip. If this were to happen, a time would come when the universe ends with infinite scale factor, likely more than 100 billion years from today, if it happened. The time of the universe's end is a sensitive function of W. Cosmologists want to better determine if dark energy density is constant or evolves, and how it evolves as a function of scale factor and/or time. A finite universe with positive curvature can contract and end in a big crunch or a big bounce. Cosmologists do not know whether our universe is finite with positive curvature, but the future of our universe will not be a big crunch, as dark energy density is higher than the curvature energy density. Again, for more information, go to the main course. I hope this video has been helpful to you. The next video will be a more terse history of our universe.